Hi everyone. Uh, Today we are going to solve this truss using the stiffness matrix method. And first thing is we need to know the stiffness matrix for each element. Okay. So the step number one is to build the element stiffness matrix. If we consider a particular truss member like this, let's say, so the definition or else how you define the truss member from which node towards which node is very important. For example, let's say this is node 1 and this is node 2, okay, and this is theta, okay. So this is your member, so this is your x-axis. So if you consider from this element from node 1 to 2, then you should consider the direction of that and the direction with the x-axis, okay. This direction, how much of an angle, okay, that direction makes with the positive direction of x-axis. That's your theta. For example, in this case it is theta. If you consider it from let's say element the same element from node 2 to node 1, then you have to consider the angle. If we draw the x-axis from here, then this is the angle it makes. So that becomes 180 plus theta, right? And this is the stiffness matrix if we consider this element. So I will write K element. So that would be the area, Young's modulus, length, so there will be two nodes, okay. So each node will have two displacements in global x direction and global y direction. So since we are considering this 2D plane truss, okay, so if we consider a node, so we'll have along global x direction u and global y direction we call it v, okay. And this is the matrix we are going to transform into a global coordinate system, okay. So this will be c squared cs cs and s squared, and this would be these four will be negative sign of this one, okay. So this is going to be minus c squared minus cs minus cs. I'll define what is this c and s, okay, and s squared. And final four items, okay, will be exactly same. C squared cs cs and s squared. This will be c squared minus cs minus CS minus S squared. So if you have a close look at this matrix, this is symmetric. Along the main diagonal, you can see the elements are symmetric. Okay, so one way to remember this matrix is to remember first four elements. For example, this. Okay, so if you consider these four elements would be exactly the negative value of this and the same. Okay, these four are same and it is the negative value of this matrix, and this will be equal with final four members, right? That's one way of keep remembering this matrix. And we denote the rows and columns like this. If you define it from first node to second element, okay, I will take it from first node to second element. So first node you will have u1 and v1. Doesn't matter, it can be even downwards, so final value will be negative in case of if you simplify it correctly, right? So this will be u2 and I'll call this v2. Okay, so you denote the rows and columns in the same manner. So this is going to be u1, v1, u2 and v2. u1, v1, u2 and v2. Okay, so we are going to have this matrix. So if you consider a simple example like this, okay, so the nodes had been already defined. So this is 1, 2, 3 and 4. So I will define it as it is. For example, if you consider it from 1 to 2, okay, element 1, from 1 to 2, element 2, element 3 is a spring. Okay, doesn't matter even if it is only having axial loads only, right? So element 2 will be from 1 to 3. Element 4 is from 1 to 4. I will take. If it is 1 to 2, so the angle would be this angle, right? 1 to 4. Check the direction 1 to 2, right? So 1 to 2, the direction is like this. With the x-axis, it makes around 135 degrees. That is theta. So this C is cos theta. Okay. C is cos theta, S is sin theta. So C squared means cos squared theta and CS means the product of sin theta and cos theta, and S squared is sin squared theta. And 1 to 3, the angle is 180. And 1 to 4, okay, for the spring, if you consider it from 1 to 4, so this will be the angle, for example, that will be 270. Okay, so we have the angles and everything. So don't worry if you don't have a member like this. So this will be very easy because this is the answer for whole AE over L. So it's given. For these members, you have to calculate that, right? For this spring, you don't know area, you don't know the Young's modulus, you don't know the length, okay? But if the spring coefficient is given, so that equal to K, right? So you only need to assemble the transformation matrix with this K, right? let's see how it's done. So the first step one is the element is stiffness matrix. So we call it for element 1. Okay, so that would be theta is 135. Okay, so that means c squared, that means cos squared theta is 0.5, and that equals to sine squared as well. And sine squared cos squared, sorry, sine theta cos theta is minus 0.5. Okay, and AE is given. Okay, AE is given, so you can calculate this one. This is K E, this is E gigapascal, so that means 10 to the power minus 9. E A, how much is A? Like 0.0005 over L. L is 5. And then the matrix, okay, 0.5 minus 0.5 minus 0.5, 0.5. So I will write only the above triangle of the symmetric part, above triangle of this matrix which is symmetric. Okay, so this will be 0.5. Okay, so that's done. And if you simplify this, you'll end up with 105 into 10 to the power 5 into this matrix. Okay, similarly, power 5. Okay, sorry, to simplify this, oh, one more thing, you can take 0.5 out, because for uh, each item is like each element, yeah, is each element is 0.5, so you can take 0.5 out, right? So which makes, so if you take 0.5 out, everything will be 1. Okay, other things are symmetric, so then it will become 10 to the power 5 and 105. Okay, similarly you can construct with element 2 as well, so it's still behind step 1. So theta was 180, so which brings you c squared is 1, s squared is 0, cs is 0. Okay, and after simplifying this, like in the previous step, like, so you will get an matrix like this. In that matrix, the original length will be 10, right? In the previous matrix, the length was 5. Other two are similar with element 2 as well. So for element 2, that will become 10. Okay. But in here, you will have only 1, 0, 0, 0. Others are. So you can't take anything from this matrix, which brings you again the same output as in the previous. Sorry, this is not 10. This is the length only, right? If you simplify this, this will be same, this will be same, this would become 10, and you can't take anything from this matrix, so which brings you the same coefficient as it is, right? Same scalar, right? Because if you take 0.5 out, okay, and this 5, okay, so that would become in the denominator, it will become 10, same as this is, right? So after simplifying this, you would get this one, right? Okay, so this is element 2, and for element 3, you know the value, right? You know this value was yeah, 2000 kilonewtons per meter. So that brings you that brings you 1000 kilonewtons means 200 so 1000, so which needs to be converted to newtons per meter, and the matrix with angle, so that would be 2270, the angle, so that would be 0 1 sorry 0 0 0 1 0 0 0 minus 1 0 minus 1 1. So this you can simplify similar to this, 20 into 10 to the power 5. So I keep 10 to the power 5 because I can bring this or move this into the matrix, right? Because when you add up these matrices, when the scalar is different outside the matrix, you can't simply add those. So for that, you need to make it similar. For example, in this case, 10 to the power 5 is common. So you need to move this 20 into the matrix. So that means you have to multiply each element by 20, multiply each element by 105. So then only 10 to the power 5 minus 10 to the power 5 will be outside here. Okay, so you need to put this 105 into the matrix, multiply each element by 105. Then you can, if you want, you can add or subtract the matrices. So this step two is to assemble the matrix, the final matrix. So we have 4 nodes, right? We have 4 nodes. Okay, so in 2D space, so that possible, it is possible to have 8 displacement considering these 4 nodes. If you consider u1, okay, u1, so that you can consider u1 v1 and u2 v2, u3 v3 and u4 v4. So we'll consider the forces at those locations. Let's call it fu1, fv1, fu2, fv2, fv3, fv3, fu3, fv3. Sorry, I don't think I have enough space. This is u1, this is v1, u2, v2, u3, v3, u4, v4. Okay, so I'm considering the sign convention, forces and the displacement, same force, the displacement and the force positive on the same side. Okay, so you this way, forces and displacements are positive. In this way, forces and displacements are positive. So this is the force matrix. Okay, so now I have to assemble the global stiffness matrix. So this will be u1, v1, u2, v2, u3, v3, u4 and v4. This is same, u1, v1, u2, v2, u3, v3, u4, v4. Okay, so how we assemble it is like, take first element. Okay, so you have now 10 to the power 5 outside, 105 inside, so each element will be 105, right? So how you going to assemble it is, right, so element 1 is from 1 to 2, so that means u1 v1, u2 v2, u from u1 v1 to u2 v2, remember it that way. So element 1 is from like this, so you can simply write as it is. So this will be -1, right? Okay, so you are going to assemble this one. Hundred point five, 105 minus 105, so outside 10 to the power 5 is waiting. u1 v1 and columns, sorry, rows u1 v u2 u1 v1 u2 v2, the same matrix which is inside, right? So you can see the row columns and the rows, right? So only these 8 displacement far only for denote the rows, right? Denote the columns. Okay, denote the columns. 13 different color u1 v1. u4 and v4. Okay, so okay, we have successfully input the element 1 matrix, right? So now we are going to consider element 2, right? For element 2, so 105 will be there. So only these 4 will be 10 to the power 5, 0. Likewise will be there, right? So this element is defined from 1 to 3. So that means u1 v1 to u3 v3, right? u1 v1 u1 v1 to u3 v3. So we can take u1 the rows u1 columns u1 v1 are these u3 v3. So take these elements. So for this element, column is u1, row is u1, column is v1. Yeah. So simply the columns and rows are u1 v1 and u1 v1, these 4 elements, like, right? Okay, so by looking these rows and columns, so for these 4 elements, columns are u3 and v3 and u1 v1. Likewise you can construct this one for u1 v1. So simply these 3, for these 4 elements, the first 4 elements of the matrix will be added, right? So these 4 are going to be added with these 4. So that means this is 0, so nothing happened. So only this would become 105 plus 105, so that will become 210, right? So others are 0, and similarly it will happen for u3 v3 as well. So there's nothing to add, to be added, right? So here the rows are not aligned. Okay, so this is 105, and this is also 0, 0, and this was 0, as I remember. Yeah. Okay, so those 4 elements are okay now. Okay, and upper triangle, so this was u3 v3 and u1 v1, so that means u3 v3 u1 v1, and it is going to be here, right? So that is negative 104 0 0. Likewise, you can place all the elements, right? Since it is symmetric, the 4 elements is going to be here. Okay, so now it's okay. U3 v3 u1. So finally it's from 1 to 4. So this is the element, this is the element 0 0 0 1. So if you place 20 inside, so this 10 to the power 5, this would be 0 0 0 and 20. Likewise, all would be multiplied by 20, and it is from u1 to 1 to 4. That means u1 v1, u4 v4. So the elements from u1 v1 and u1 v1 will be here 0 0 0 20. So 20 will be added here, right? For example, you can even draw that matrix like this, right? Divide it into 4. So this is from u1 v1, u4 v4. This is the part which is to be added, u1 v1, and these rows are u1 v1. So these 4 elements will be added to these 4 elements, because it is also u1 v1, u1 v1. These 4, u4 v4 and u4 v4, will be added here. So you can check the row and column, easily construct this u1 v1, column and row. Okay, column and row. This is a u4 v4 and u1 v1, u4 v4 and u1 v1. That will be here, and similarly it will be here, the other 4. Okay, so what is going to happen is you will add 20 here, so that will be 125. Okay, so here 0 0 0 minus 20, as I remember, 0 0 0 minus 20, 0 0 0 20. Okay, if you don't have anything for remaining elements, put 0 to each one, because there's no contribution. You can't keep it empty. Place 0. So this is the global stiffness matrix of the truss, entire truss. And these are for denoting. So this is the displacement matrix, the correct one, u1, v1 up to v4. So you will see something, right? These are supports, right? So which means here, pin support, pin support, pin support, right? So that means u1, v1 are, sorry, u and v displacement at 2 3 4 are 0, because there's a support, right? So these are 0, u2 v2, u v2, u3 v3, u4. These 6 are 0, right? So that means you can eliminate that rows and columns. So I'm going to eliminate. Sorry. And same as the columns. Okay. Finally, you will be ended up with this matrix, right? Okay. So if you consider FU1, FV1 will be 10 to the power 5, 210 minus 105 minus 105, 125 Q1 and V1. So you know what are the forces, because those are at this point, right? So there's no force along U direction, but there's force in Y direction, but it is in downward direction. So that means negative 50. So that means 50,000 newtons, right? This is 0. This is 50,000 minus. Why? It is in downward direction. This is 50,000. Okay. 10 to the power 5, not plus 5, plus 5. Okay. So you can bring this 5 here. Okay. So if you divide each element by 10 to the power 5. So each element will be if you divide by 10 to the power 5, this is still 0. This would be minus 0.5, right? So you have to let this is A. So you are going to multiply A inverse by this matrix to obtain the displacement, where you will obtain Q1 and V1 as, if you get it, you will obtain, this is minus 0.0034 meters, and the second one is minus 0.068 So all these are in meters. So that means 4.4 millimeters and 6.8 millimeters. Okay. So these are negative, right? So that means the displacement is actually in this direction and this direction. This direction 3.4 millimeters, this direction 6.8 millimeters, right? So now we have the displacements. Okay. So if you plug the displacements, right? If now you know the displacement, if you plug displacements to here, you can calculate each force by this matrix. So we'll use Excel to calculate that. So we are now at the step 3. 3, which calculate the forces back. And we know already Fu1 is 0 and if V1 is minus 50,000 newtons. Okay, I did not put it because we already know the displacements. Okay, this is K, the matrix K, and this is the scalar, which is common to the matrix 10 to the power 5, right? Since we know these two displacement, we can calculate, multiply these two matrices and multiply with this scalar. First, I will multiply these two matrices. You can use matrix multiplication. You remember to press Control and Shift and enter together, right? And you will obtain, it is almost, so you have to multiply everything by, so this is, I'm multiplying by 10 to the power 5, so you will get almost 50,000. So the force at node 2 is, right, minus 36, right? So if I draw these things, okay, so we have these forces we already know, first two, right? If I draw it along this, we know we don't have any forces 0, so it will calculate back our values, right? 0, and it is almost minus 50,000, right? So for element 2, right, element 2, we have in this direction 36.2 kilonewtons, and this direction that same 36.2 kilonewton, right? And at this way you have 36.2, right? This is 0, and here you have 0, here 13.7. If I need to calculate, since I know the forces at the supports, right? This is 45, at this angle is 45, right? I can take the component and find the forces at any node. For example, it's like this. This is 36. Let's say this is F. So this was also 36.2 because it was same, and this was 45, and it was actually in this direction, right? Minus 32.6. So if I take components along this direction, right? So both will have same components. So that will be 2F into since theta is 45, cos theta and sin theta are equal, right? So if this is theta, this will also be theta. It doesn't matter, cos theta and sin theta are equal. So I can take 2F cos theta, cos 45. So that would bring you 2 into cos 45 means root 2F. So F is 36.7, so which brings you to 51.2, right? In this way, so that material should resist in this way, right? So that will be a tension, right? Equal to 51.2 kilonewton. And if you divide it by the area, 51.2 divided by the area, 0.0005. So that will be around 102 megapascals. Similarly, you can calculate the stresses at this member as well, right? Second member. This is how you normally do a truss. So for this part, when you calculate the forces, the member forces, tension and compression, there's a method to transform it back and take it. But in this method, if you know the nodal forces, you can simply take the components at any node and find the compression or tension using the equilibrium at this joint, and using the knowledge that you gain from the high school, right? Okay, thank you.